Welcome back, Chemistry 30. This is the third booklet in the acids and bases section. What is pH? So in this section, we'll be looking at defining and providing an example of the ion product constant for water, pH, and POH. Write the ion product expression for the dissociation of water. Recognize the relationship between H and OH. In aqueous systems, show how adding H or OH influences the equilibrium of water's dissociation. Calculate the hydrogen ion concentration, express the hydrogen ion concentration as a pH value, explain how the logarithmic scale is different from the arithmetic scale, explain the meaning of pH and POH, relate pH and POH to the ion product constant for water, and calculate pH and POH. So first of all, the equilibrium equation for when water dissociates looks like this. So if you look, water, of course, breaks down into an equal amount of H pluses and OH minuses. The acid characteristic and the base characteristic balance each other out. And another thing to note is that the arrow is larger to the left, meaning that water mostly exists as H2O, but a small amount exists as this form over here. What is the equilibrium constant? So if I was to figure out the KEQ, first of all, it's products over reactants. And similarly to the other booklets, since these change very slightly compared to water, we can think of water as being a constant term, combine it with KEQ, and come up with what we refer to here as the water constant, or KW, which is the product side there. H plus multiplied by OH minus. And in an aqueous solution, that works out to be 1.0 times 10 to the minus 14. Okay. If we look at how Le Chatelier's principle affects this, if we take a look at water, and if we added something that had an acid characteristic, it gave off H plus ions. If we increase the H plus ions, of course, the response would be to try to decrease it, and it would do that by shifting to the left. And as a result of that, the concentration of water would increase, and the OH minus ions would get used up as well as the H plus ions. So it would shift to the left, using up the hydroxide ion concentration, so you'd end up with more H's in the long run. Okay, if we look at some examples here, dealing with that. So first of all, if you look at the top here, things that are solutions that are neutral, of course, have an equal amount of H pluses and OH minuses. Acidic has more H's than OH's, and basic has more H's than H pluses. So in each of these, calculate the hydrogen ion or the hydroxide ion concentration in each. So basically we are using the ion product constant, this equation right here. H multiplied by OH yields 1.0 times 10 to the minus 14. So here we have the hydrogen ion concentration. So to figure out the hydroxide ion concentration, you can see here that it's just simply writing in my H. Whoops, went the wrong way there. So we know what H is. We're looking for OH. So we would, to isolate hydroxide, we would divide by my H concentration on each side. So you can see that's what I did there. I kind of ran out of room here, so I didn't show all the steps. So divided by my H concentration of 1.0 times 10 to the minus 14, divide the right-hand side by it as well, and we get that. Now, stating it as to whether it's acidic, basic, or neutral, don't fall into the trap of seeing this 10 and thinking it's bigger than a 4, therefore it's going to be basic because I have more OH. Be aware that this represents how many decimal places the decimal is shifted to the left. So here, -4, just 4 places to the left. Here, -10 places to the left. So this one's a lot smaller. My H plus ions are bigger, therefore it's acidic, since my hydrogen ion concentrations are bigger than the OH minus. Okay, maybe pause the video. You try this one now. This time it's vice versa. You're given hydroxide ion. You figure out hydrogen ion concentration. Okay, if you had a chance to do that, so this time we're going to divide by hydroxides. And if we look there, we get our number 1.0 times 10 to the minus 14. divided by 1.3 times 10 minus 2, and we get this. Now 10 to the negative 13 versus 10 to the negative 2, this is a lot bigger, so it is basic. Okay, so since we were dealing with, we could see these numbers are really, really small. So to give numbers that, you know, like human beings like to work with, larger numbers, the pH scale is developed. pH stands for potency of hydrogen ions, and that number that we use there, we actually use the logarithmic scale, or the log function, to figure that out. We take the negative log of H plus ions, and we'll see what that means in a second here. Now, if we take a look at the logarithmic scale, you likely have seen this, or even before we look at that. The arithmetic scale we know goes up by 1, 0, 1, 2, 3, 4, 5, etc. We can look at it that way. If I was comparing the logarithmic scale to an arithmetic scale that goes up by 1, for every movement of 1 on the arithmetic scale, the logarithmic scale goes up by a factor of 10. So 4 to 5, that's 10 on the logarithmic scale. 4 to 7, that's times 10 times 10 times 10, so it's actually 1,000. And you've likely heard of this before when you're looking at the Richter scale for measuring earthquakes, an earthquake of 6 versus 5. Even though it's only increases by 1 on the arithmetic scale, it's times 10 on the logarithmic scale. So how severe is it? It's 10 times more severe at 6 than at 5. So that's kind of how that scale works. And something that you would have taken in earlier grades is the pH scale, going from 0 to 14. 7 is smack dab in the middle. It's considered neutral. Things that have acidic characteristics are less on the scale. Things that are basic are higher on the scale. And something else that I've thrown here is the pOH scale. It runs exactly backwards. The potency of hydroxide ions. And you can see these red bars here. The reason why I have them is that you can see that the pH and the pOH always add up to be 14, where this relationship comes from. 8 and 6, 9 and 5, etc., etc. So pH scale goes from 0 to 14, pOH goes from 14 back down to 0 in a decreasing fashion, and we can see the first relationship there between the two. Okay, so if we look at here, some questions. Calculate the pH of these solutions. So if we look at the first one here, 1.0 times 10 to the minus 14. So the pH is the negative log of my hydrogen ion concentration. So we just type that number in. Now on your calculator, of course, the times 10 to the part can be found with your EXP or your EE button. So take the negative log of that and we get 4.0. And of course that is lower than 7 on the pH scale, so it is considered acidic. Now the interesting thing here, because of the form this number is in, our pH is actually equal to this exponent here. Okay, I'll try another one with you. Let's try OH this time. So we can take our OH concentration. We need to figure out the pH, which means we need to know the hydrogen ion concentration first. So of course H multiplied by OH gives us 1 times 10 to the minus 14. So we can substitute our number here for hydroxide, divided, we get that. And again, take the negative log of my H plus ion concentration and I get 2.0. Okay? What I'll get you to do is to try the ones over here. Try B and D beside here, and you can tune into part 2 of the video to see how you did. Okay, we'll see you soon.